What if everything we think we know about the universe is just the tip of the iceberg? Picture standing at the edge of an endless cosmic ocean, where every discovery sends ripples through the very fabric of reality. The universe isn't just vast, it's alive with secrets that defy logic, bending the rules of physics and rewriting our understanding of existence itself. And today, we're diving deep into 30 of the most astonishing cosmic discoveries ever made, each one a puzzle piece in a grander mystery that's still unfolding. Think about the last time you looked up at the night sky and felt that humbling sense of wonder. Now imagine that feeling amplified by 1,000, because what astronomers and physicists are uncovering out there isn't just beautiful, it's mind-bending. Black holes that sing, galaxies that shouldn't exist, particles that teleport, these aren't plot twists from a sci-fi novel. They're real phenomena documented by cutting-edge science, and they're challenging everything we thought was possible. The deeper we probe, the more the universe seems to whisper, "You haven't seen anything yet." This journey isn't just about listing bizarre facts, it's about stepping into a world where the impossible becomes routine. A place where time loops back on itself, where invisible forces shape galaxies like cosmic hands molding clay, and where the very emptiness of space crackles with hidden energy. These discoveries aren't just reshaping textbooks, they're redefining what it means to explore. So if you've ever wondered what lies beyond the edge of human knowledge, or felt that itch to uncover the universe's best-kept secrets, you're in the right place. Buckle up, by the time we're done, the night sky will never look the same to you again. One of the most baffling cosmic mysteries isn't some colossal explosion or a swarm of stars, it's the absence of them. Lurking in the constellation Boötes lies a terrifying expanse of nothingness so vast it defies comprehension. The Boötes Void stretches an unfathomable 330 million light-years across, a cosmic desert so empty that if our Milky Way sat at its center, we wouldn't have discovered other galaxies existed until the 1960s. That's right, an entire civilization could have thrived here for millennia without realizing they were alone in the universe. This isn't just a quiet corner of space, it's a glaring anomaly that makes astronomers question everything. According to our best models, the universe's structure should resemble a sprawling cosmic web, with galaxies clustered like interconnected threads. But the Boötes Void is a gaping hole in that web, a place where the rules seem to break. Imagine shaking a snow globe and watching the glitter scatter evenly except for one bizarre, empty bubble that refuses to fill. That's the level of weird we're dealing with. So how did this great nothing come to be? Some theorists suggest it's the scar of an ancient collision between universes in the multiverse, a sort of cosmic bruise left behind. Others propose it's the work of supermassive black holes merging long ago, their unfathomable gravitational waves scouring the region clean like a celestial vacuum. But the most spine-tingling idea, that advanced civilizations could have harnessed the energy of entire galaxies, leaving behind this eerie void as evidence of their unimaginable power. Whatever the truth, the Boötes Void forces us to confront an unsettling possibility. There are places in the universe where the silence isn't just profound, it's unnatural. And if one such abyss exists, how many more are waiting to be found? Now imagine a signal so powerful it could outshine an entire galaxy, but only for a fraction of a second. Fast radio bursts, or FRB, are exactly that, cosmic flashes of radio waves so intense they release more energy in milliseconds than our sun does in decades. And here's the kicker, we still have no idea what's causing them. Since their accidental discovery in 2007, these bizarre signals have been popping up across the universe like cosmic Morse code, vanishing before we can trace them back to their source. What makes FRBs truly maddening is their unpredictability. Some fire once and never repeat, like a celestial one-hit wonder. Others pulse on a loop, flashing with clockwork precision every few weeks or months. One particularly famous repeater, FRB 1218, even follows a 157-day cycle, active for 90 days, then silent for 67. It's as if the universe is teasing us with a puzzle that changes its own rules. So where are these signals coming from? The leading suspect is magnetars, super-dense, highly magnetic neutron stars that occasionally unleash violent flares. In 2020, astronomers caught one red-handed when a magnetar in our own galaxy emitted an FRB-like burst. But there's a problem. Most FRBs originate far beyond the Milky Way, and their signals are often distorted in ways that suggest they've passed through extreme environments, like the halos of distant galaxies or the turbulent outskirts of black holes. Could these be natural cosmic lighthouses, or is there something even stranger at play? Then, of course, there's the elephant in the room, alien civilizations. Some scientists argue we shouldn't dismiss the possibility that advanced beings might be using FRBs to communicate, or even power light-sail spacecraft across interstellar distances. After all, the precision of repeating bursts does feel eerily intentional. But here's the twist. The most distant FRB ever detected traveled 8 billion light-years to reach us, meaning it erupted when the universe was half its current age. If this was a message, it was sent by a civilization that likely vanished before Earth even formed. The truth is, FRBs are more than just cosmic static. They're windows into the universe's most extreme environments. Every time we detect one, it's like intercepting a postcard from a place where matter and energy behave in ways we can barely fathom. And with new telescopes like Canada's CHIME scanning the skies 24/7, we're on the verge of uncovering whether these bursts are the universe's way of screaming into the void, or whispering secrets we're only beginning to decipher. Hold on to your sense of cosmic direction, because what if I told you the universe isn't just expanding, it's being pulled? Picture hundreds of galaxy clusters, each weighing trillions of suns, all streaming toward a single point in space like moths to a flame. This isn't science fiction, it's a real phenomenon called dark flow, and it's one of the most unsettling mysteries in modern cosmology. The story begins in 2008, when astronomers studying the cosmic microwave background, the afterglow of the Big Bang, noticed something bizarre. Galaxy clusters weren't just drifting randomly with the universe's expansion. They were racing in unison toward a region near the constellations Centaurus and Vela at speeds exceeding 2 million miles per hour. It's as if some invisible hand had reached into the cosmos and given them a collective shove. The kicker, there's nothing there, no supercluster, no black hole, no known structure massive enough to exert such a gravitational tug. This discovery sent shockwaves through the scientific community. Some dismissed it as a statistical fluke or a calibration error in the data. But repeated studies, including observations from NASA's Wilkinson microwave anisotropy probe, kept confirming the same eerie motion. The leading theory that whatever's pulling these galaxies lies beyond the edge of the observable universe. Think about that for a second. Our observable cosmos spans 93 billion light-years, containing every star, planet, and speck of dust we'll ever see. But dark flow suggests something even more colossal, perhaps an entirely separate universe, or a mind-bending concentration of mass exerting gravity from a place we can't observe, measure, or even comprehend. Of course, not everyone's convinced. Critics argue that dark flow could be an artifact of incomplete data, or an undiscovered flaw in our understanding of gravity. But if it's real, the implications are staggering. It would mean our universe isn't just one island in a multiverse. It's being actively shaped by forces from outside our cosmic horizon. Some theorists even speculate these flows could be scars from a collision with another universe during the Big Bang, like cosmic bumper cars leaving behind invisible dents in spacetime. The most haunting possibility, this motion might be evidence of structures so vast they dwarf our entire cosmos, structures that could rewrite the rules of physics as we know them. For now, dark flow remains a tantalizing enigma, a reminder that even the mightiest galaxy clusters might just be leaves floating on a river whose source we'll never see. And if that doesn't make you question everything you thought you knew about the universe, well, just wait. The next discovery will. It was just an ordinary evening at Ohio State University's Big Ear radio telescope on August 15, 1977, until the universe decided to send a postcard. For 72 electrifying seconds, a narrowband radio signal blasted through the static, so precisely aligned with the frequency hydrogen emits in space that it seemed engineered to catch our attention. When astronomer Jerry Amon circled the alphanumeric code 6EQUJ5 on the printout and scribbled "Wow" in the margin, he unknowingly named one of the most tantalizing cosmic mysteries of all time. The wow signal wasn't just loud, it was suspiciously perfect. Broadcasting at 1420 MHz, a frequency shielded from natural interference by international agreement, it had all the hallmarks of an intentional transmission. Even stranger, it originated near the Chi Sagittarii star group, a region with no known planets or obvious cosmic fireworks. Scientists scrambled to find a natural explanation: a passing comet, a rogue satellite, even a glitch in the equipment, but 47 years later, not a single theory holds up. The signal vanished as abruptly as it appeared, leaving behind a trail of unanswered questions and a haunting possibility. Had we just missed a cosmic hello? What followed was a decades-long detective story. Teams scoured the same patch of sky over 8,000 times with far more sensitive equipment, listening for even a whisper of repetition. Nothing. In 2012, the Arecibo Observatory beamed a high-powered response toward the signal's origin, a symbolic gesture, since any potential senders would be over 1,500 light-years away. Even today, SETI researchers treat the wow signal like a sacred text, analyzing every nuance for clues. Was it a burst from an alien megastructure, a natural phenomenon we've yet to understand, or something even weirder, like a message meant not for us, but merely passing through us on its way elsewhere in the cosmos? What makes this enigma endure isn't just the absence of answers, it's what the signal represents. In a universe where we've catalogued gravitational waves and photographed black holes, this 72-second blip remains a humbling reminder of how little we truly know. The wow signal is less about what we heard and more about what we might have heard, a fleeting glimpse into a cosmic conversation that could rewrite humanity's place in the universe. And until we detect its echo, it stands as both our greatest near miss with the unknown and a beacon urging us to keep listening. In the constellation Cygnus, about 1,400 light-years from Earth, a star named KSE 8462852 behaves like nothing else in the known universe. Nicknamed Tabby's star after astronomer Tabetha Boyajian, who first documented its bizarre activity, this flickering enigma dims by up to 22% at irregular intervals, as if something colossal is passing in front of it. Not a planet, not a dust cloud, something far stranger. When Kepler Space Telescope data revealed these erratic dips in 2015, scientists were stunned. Planets, even gas giants, typically block less than 1% of a star's light during transit. But Tabby's star doesn't just dip, it plunges with no predictable rhythm. Some dimming events last days, others stretch for weeks. At one point, the star's overall brightness dropped a staggering 14% over a century, as if it were slowly being shrouded in shadow. The most dramatic event, a 72-hour period where it dimmed 22%, equivalent to a swarm of Jupiter-sized planets crossing its surface in tight formation, which we'd easily detect. But there's no such swarm. Cue the alien megastructure hype. One theory suggested an advanced civilization might be constructing a Dyson swarm, a colossal array of energy-harvesting satellites encircling the star. The irregular dips could reflect construction phases, with panels occasionally aligning to block massive amounts of light. It's a tantalizing thought, but science demands harder evidence. So researchers turned to natural explanations. maybe a family of shattered comets or asteroids pulverized by a cosmic collision was creating a swirling debris field. Or perhaps the star recently devoured a planet, vomiting dust clouds that now orbit chaotically. Yet every hypothesis hits a wall. Dust, for instance, should scatter infrared light, but Tabby's star shows no excess infrared. A black hole's gravity bending light, no telltale lensing effects appear. Even the most exotic natural models struggle to explain both the deep, aperiodic dimming and the century-long fade. The truth is, Tabby's star isn't just challenging our ideas about alien engineering, it's revealing how much we still don't understand about stellar behavior. New observations suggest magnetic activity or stellar heartbeats could play a role, but the data remains stubbornly ambiguous. Every time we think we've pinned it down, the star throws another curveball, as if taunting us from across the galaxy. Here's the kicker: Tabby's star might not be alone. Astronomers have since identified a handful of similar Dipper stars, each with its own erratic light patterns. Could these be part of a previously unnoticed cosmic phenomenon, a new class of variable stars, or evidence of processes we've yet to imagine? Until we crack the code, Tabby's star stands as a humbling reminder that even the most familiar cosmic objects can harbor secrets that rewrite the rules. And whether the answer involves dust, aliens, or something entirely unforeseen, one thing's certain: the universe loves keeping us guessing. In a universe teeming with hundreds of billions of galaxies, each containing trillions of stars, the math suggests we should be drowning in extraterrestrial neighbors. The Milky Way alone could host millions of civilizations, so why does the cosmos feel like a ghost town? This is the Fermi Paradox, a puzzle so profound it forces us to confront whether we're missing something fundamental about reality itself. The paradox takes its name from physicist Enrico Fermi, who famously blurted out, "Where is everybody?" during a casual lunch conversation in 1950. His point was razor-sharp. If life arises easily, advanced civilizations should have colonized the galaxy by now. Even at sublight speeds, a single spacefaring culture could spread across the Milky Way in just a few million years, a blink in cosmic time. Yet after decades of listening with radio telescopes, scanning for megastructures, and probing Mars for microbes, we've found exactly nothing. Not a single whisper, not a footprint, not even a speck of alien algae. Possible explanations range from the comforting to the chilling. The Great Filter theory suggests some near-insurmountable hurdle prevents life from advancing, whether it's the improbability of abiogenesis, the inevitability of self-destruction through nuclear war or climate collapse, or some unseen cosmic catastrophe that wipes out civilizations before they can spread. If the filter lies in our past, we might be miraculously lucky. If it's ahead of us, humanity's future could be far bleaker than we imagine. Then there's the zoo hypothesis, the idea that advanced species deliberately avoid contact, treating Earth like a protected wildlife reserve. It's a poetic notion until you consider what kind of power structure would enforce such silence galaxy-wide. Other solutions get even weirder. Maybe interstellar travel is impossible due to hidden physics, or civilizations inevitably retreat into virtual realities, losing interest in the outside universe. There's even the dark possibility that predatory aliens systematically eliminate competitors, forcing survivors into radio silence. But here's what truly unsettles: the paradox might not be about them, it might be about us. Our search assumes aliens think like humans, using technology we'd recognize. What if they communicate through neutrino pulses or quantum entanglement, channels we're only beginning to explore? Or worse, what if we're like ants at a picnic, surrounded by cosmic activity too advanced for us to perceive? The Fermi Paradox isn't just an astronomy problem, it's a mirror. Every possible answer forces us to reevaluate humanity's place in the cosmos and our own future. Whether the silence means we're alone, doomed, or simply ignorant, one thing's certain: the universe isn't playing by the rules we expected. And until we crack this puzzle, the stars will keep their secrets just out of reach. Deep in the direction of the constellations Centaurus and Hydra, our galaxy isn't just drifting aimlessly, it's being hauled through space at over 1 million miles per hour towards something we can't even see. This cosmic tractor beam is known as the Great Attractor, a gravitational anomaly so powerful it's pulling not just the Milky Way, but hundreds of thousands of other galaxies along with it. And here's the twist, we're staring straight at it, yet it remains shrouded in mystery, hidden behind what astronomers call the zone of avoidance. This isn't your run-of-the-mill celestial landmark. The zone of avoidance is a thick band of dust, gas, and stars, the crowded central plane of our own galaxy that blocks nearly 20% of the sky from our telescope's view. It's like trying to peer through a fogged-up windshield while driving toward a distant landmark. Early observations suggested the Great Attractor might be a massive supercluster, a dense knot of galaxies with enough gravity to tug on us. But as our technology improved, we realized this was no ordinary cluster. It was just the tip of the iceberg. X-ray and infrared telescopes slicing through the cosmic fog revealed something even larger lurking behind it. The Laniakea supercluster, a sprawling filament of galaxies 500 million light-years wide, with the Great Attractor acting as its gravitational heart. Picture a vast cosmic watershed where galaxies flow like rivers into a valley we can't yet fully map. But here's where things get weird. Even Laniakea's immense gravity can't fully explain the motion we're seeing. Some researchers argue there's something even more massive, perhaps a cluster of dark matter or an unseen structure beyond our current detection, pulling us deeper into the cosmic web. Theories abound. Could it be an intergalactic highway shaped by dark energy, a remnant of an ancient collision between universes, or evidence of forces we haven't even discovered yet? Every new observation adds layers to the puzzle. Recently, astronomers discovered the Vela supercluster, another massive structure hiding in the zone of avoidance which might share the gravitational load. But the Great Attractor's pull is so strong that some galaxies are being yanked into it faster than the expansion of the universe should allow, a violation of cosmic rules that leaves physicists scratching their heads. What makes this mystery so thrilling is what it represents, a humbling reminder that even as we map the cosmos, the universe keeps its grandest blueprints just out of sight. The Great Attractor isn't just pulling galaxies, it's pulling our curiosity, dragging us toward questions we're only beginning to formulate. And until we crack the code of what lies behind that dusty veil, one thing's certain: the universe's greatest surprises might be hiding in plain sight, waiting for us to look closer. On October 19, 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted something streaking through our solar system that shouldn't have been there. A needle-thin object moving too fast to be bound by the sun's gravity, tumbling end over end like a cosmic javelin hurled from another star. Oumuamua, as it came to be called, was the first confirmed interstellar visitor ever detected, and it shattered every expectation we had about how objects from beyond our solar system should behave. Within days, telescopes worldwide swiveled to track it, but what they saw only deepened the mystery. This wasn't just another asteroid or comet. Oumuamua's shape alone defied logic, a bizarre, flattened pancake or cigar-like structure at least 10 times longer than it was wide, unlike any natural space rock we've seen. Its surface, reddish and oddly reflective, showed no signs of the icy coma that typically surrounds comets. Yet the real shock came when astronomers realized it wasn't just coasting, it was accelerating. As it hurtled away from the sun, Oumuamua sped up slightly, as if pushed by an unseen force. Comets sometimes exhibit non-gravitational acceleration when sunlight vaporizes their ices, creating a jet-like thrust. But Oumuamua left no visible trail of gas or debris. So what was propelling it? The scientific community split into warring camps. One faction argued it was an exotic type of comet with hidden ices that vaporized in ways we couldn't detect. Others proposed it might be a shard of a Pluto-like planet, torn free by a cataclysmic collision and sent careening across the galaxy. Then came the bombshell hypothesis from Harvard astrophysicist Avi Loeb: could Oumuamua be artificial? A light sail, a thin, reflective spacecraft powered by starlight sent by an intelligent civilization. The idea wasn't entirely far-fetched. Humanity's own light sail experiments, like the Breakthrough Starshot project, envision similar technology for interstellar travel. Critics dismissed the alien probe theory, pointing out that extraordinary claims require extraordinary evidence. Yet even the most conservative explanations left gaping holes. If Oumuamua was a comet, why no outgassing? If it was a rocky asteroid, how did it accelerate? The more we learned, the less it fit any known category. By the time telescopes could train their full power on it, the object was already too distant, vanishing into the void like a ghost ship taking its secrets with it. What lingers isn't just the puzzle of Oumuamua's identity, but the unsettling implication behind it. For centuries, we've assumed interstellar visitors would resemble the comets and asteroids we know. But this silent passerby proved the universe is far stranger than our models predicted. If one such anomaly slipped through our cosmic neighborhood, how many others have we missed? And when the next visitor comes, will we be ready? There's a faint afterglow from the birth of the universe that permeates every corner of the cosmos. A fossilized echo of the Big Bang called the cosmic microwave background, or CMB. This ancient light should be random, a chaotic snapshot of the universe's fiery infancy. But when scientists mapped its subtle temperature variations, they stumbled upon something that sent chills down their spines. The fluctuations weren't just uneven, they were aligned with our solar system in a way that defies all odds. Dubbed the axis of evil, this eerie pattern shouldn't exist, and yet there it was, whispering that we might be at the center of something far stranger than we ever imagined. The Copernican principle, the idea that Earth isn't special or central in the universe, has been a cornerstone of astronomy for centuries. From Galileo to Hubble, every major discovery has reinforced our cosmic mediocrity. We orbit an average star in an unremarkable galaxy, one of trillions. But the axis of evil throws a wrench into that worldview. The CMB's hot and cold spots aren't scattered randomly. They loosely trace a plane that aligns with our solar system's ecliptic, as if the universe itself is subtly nodding in our direction. The odds of this happening by chance, less than 1 in 1,000. At first, researchers assumed it was an artifact of measurement errors or telescope calibration. But as more precise satellites like Planck mapped the CMB with exquisite detail, the alignment persisted. Some proposed exotic physics. Maybe the universe is finite and smaller than we thought, looping back on itself in a way that creates illusions of alignment. Others suggested a primordial magnetic field or quantum fluctuation frozen into spacetime during the Big Bang. But the most unsettling possibility, that we're seeing evidence of a pre-existing structure beyond our universe, something whose gravitational imprint warped the CMB like a fingerprint pressed against the glass of reality. Critics argue the axis of evil might just be a statistical fluke, a cosmic Rorschach test where humans see patterns in noise. But the longer it lingers unexplained, the harder it becomes to dismiss. If it's real, the implications are revolutionary. It could mean our universe isn't isotropic uniform in all directions, as the standard model assumes. There might be a preferred direction woven into the fabric of space-time, a cosmic north that points straight at us. What makes this so unnerving isn't just the potential violation of cosmological principles. It's the quiet suggestion that after centuries of demoting Earth from the center of creation, we might have to grapple with the idea that we're not entirely insignificant. Maybe the universe isn't indifferent to our existence, or worse, maybe we're seeing the shadow of something far larger, a structure or force that predates reality as we know it. The axis of evil doesn't just challenge our models, it dares us to ask whether we've been reading the cosmos wrong all along. and until we crack its code, it remains one of the most tantalizing and terrifying hints that the universe might still have secrets even bigger than we've dared to dream. In the vast cosmic dance of galaxies, dark matter is supposed to be the invisible choreographer shaping the universe with its gravitational pull. According to our best simulations, the Milky Way should be surrounded by hundreds of small satellite galaxies, each tethered to our own by dark matter's unseen threads. But when astronomers actually count them, the numbers don't add up. We've only found about 60. So where are the rest? This glaring mismatch, known as the missing satellites problem, has become one of the most stubborn puzzles in modern astrophysics, shaking our confidence in the very models that define how galaxies form. The trouble starts with the lambda cold dark matter model, or lambdactum, the reigning framework for understanding cosmic structure. It predicts that dark matter should clump together in halos of varying sizes, with smaller halos swarming around larger ones like bees around a hive. These halos act as gravitational seeds, pulling in gas to form stars and eventually dwarf galaxies. Yet when we peer into our galactic backyard, the expected swarm of satellites simply isn't there. The discrepancy is so stark it's been dubbed the small-scale crisis, forcing scientists to ask, are our models wrong, or are we just not seeing something right in front of us? One possibility is that the missing satellites are there just too faint to detect. Dwarf galaxies born in the smallest dark matter halos might be so dim, their stars scattered so thinly that they blend into the cosmic background like ghosts in a fog. Recent discoveries support this idea. Ultra-faint dwarfs like Segway 1 and 2, found only in the past decade, contain fewer than 1,000 stars apiece, yet they're bound by dark matter halos as massive as the Small Magellanic Cloud. If these elusive galaxies are the norm rather than the exception, we might just need better telescopes to find them. The Vera C. Rubin Observatory, set to begin scanning the skies in the next few years, could reveal hundreds more hiding in plain sight. But there's a darker twist. Some theorists argue the problem isn't with our eyes, it's with our physics. What if dark matter isn't as cold as we think? The standard model assumes dark matter particles move sluggishly, allowing them to clump easily. But if they're warmer, more energetic, they'd smooth out small-scale structures, preventing dwarf galaxies from forming in the first place. Alternatively, dark matter might interact with itself or with ordinary matter in ways we haven't accounted for, sculpting the universe differently than our simulations predict. Then there's the wild card, cosmic reionization. In the universe's fiery youth, intense ultraviolet radiation from the first stars may have stripped gas from tiny halos before they could form stars, leaving them dark and nearly invisible today. If true, the Milky Way could be cloaked in a swarm of failed galaxies' dark matter halos without stars, silently orbiting in the shadows. Projects like the Dark Energy Survey are hunting for these ghosts by tracking subtle distortions in starlight, their gravity betraying their presence. The stakes couldn't be higher. If the missing satellites problem stems from flawed models, it could mean rewriting decades of cosmological theory. But if the satellites are merely hidden, their discovery would offer an unprecedented look at dark matter's fingerprints on the smallest scales. Either way, this cosmic game of hide and seek is far more than academic. It's a test of whether we truly understand the invisible scaffolding that holds the universe together. And with every new dwarf galaxy spotted or ruled out, we're one step closer to knowing whether the fault lies in our telescopes or in our fundamental grasp of reality itself. Imagine throwing a book into a fire, the pages burn, the ink vanishes, but in theory, all that information still exists as smoke and ash. Now replace the fire with a black hole, and suddenly the rules of physics break down. This is the heart of the black hole information paradox, a puzzle so profound it pits Einstein's theory of gravity against the bedrock principles of quantum mechanics. And the man who started it all, Stephen Hawking, with a revelation that shook the foundations of modern physics. In 1974, Hawking made a startling prediction: black holes aren't completely black. They emit radiation now called Hawking radiation, slowly evaporating over eons until they vanish entirely. But here's the catch: according to quantum mechanics, information about particles that fall into a black hole can't be destroyed. Every electron, every proton carries data that should in some form persist. Yet Hawking's math suggested that as a black hole evaporates, it takes that information with it into oblivion. It's like burning that book and having the ashes disappear too, a fundamental violation of quantum theory's sacred law: information must be preserved. This paradox launched a 50-year war in theoretical physics. At stake, nothing less than our understanding of reality. On one side, Hawking's camp argued information truly vanishes, meaning quantum mechanics is incomplete. On the other, rebels like Leonard Susskind proposed wild solutions to save the information. One idea: that black holes aren't destroyers but ultimate scramblers, encoding everything they swallow onto their event horizons like cosmic hard drives. Picture a hologram where the 3D interior of a black hole is secretly projected from 2D data on its surface, a concept called the holographic principle. Then came the firewalls. In 2012, a group of physicists suggested that the event horizon might be a raging wall of energy, incinerating anything that crosses it. This would preserve information, but at a bizarre cost. Astronauts falling in wouldn't experience the smooth spacetime Einstein predicted. They'd be vaporized instantly. The backlash was immediate. Firewalls violated relativity's core tenet that freefall should feel like floating in empty space. Suddenly, the paradox had morphed into a three-way clash between quantum theory, gravity, and common sense. Recent breakthroughs only deepened the mystery. In 2016, Hawking himself shifted gears, proposing that information might escape via soft hair, subtle quantum imprints on a black hole's horizon. Meanwhile, advances in string theory and quantum entanglement hint that information could be teleported out via hidden connections between particles inside and outside the hole. But the real twist came in 2019, when physicists calculated that reconstructing scrambled data from a black hole would require a computer larger than the universe itself, a practical impossibility. Why does this matter beyond theoretical squabbles? Because the paradox is a litmus test for any theory of quantum gravity. If we can't explain how information survives a black hole, we can't unify relativity and quantum mechanics, the holy grail of physics. It's a battle playing out in chalkboard equations and thought experiments, with the universe itself as the ultimate referee. And until we solve it, black holes will remain more than cosmic vacuum cleaners. They're cosmic lockboxes, guarding secrets that could rewrite the rules of existence. The question isn't just whether information escapes, it's whether we're smart enough to decode the message. When astronomers mapped the distribution of gamma-ray bursts across the cosmos, they expected to see a random sprinkling, proof that these violent explosions were scattered evenly throughout the universe. Instead, they stumbled upon something that made their jaws drop, a structure so vast it shouldn't exist under any known rules of cosmology. Meet the Hercules-Corona Borealis Great Wall, a staggering filament of galaxies stretching 10 billion light-years from end to end, roughly 1/9 the observable universe. To put that in perspective, if our Milky Way were the size of a grain of sand, this titanic wall would span the length of 20 football fields, and its very existence defies everything we thought we knew about how the cosmos organizes itself. The problem isn't just its size, it's the age. According to the principle of cosmic inflation, the universe expanded so rapidly after the Big Bang that matter should be distributed uniformly at the largest scales. Structures bigger than about 1.2 billion light-years simply couldn't have had time to form under gravity's influence. Yet here we are, staring at a galactic superstructure nearly 10 times that limit, woven together like some cosmic spiderweb. It's like finding a single snowflake the size of a continent. a fluke so outrageous it threatens to unravel our models of the universe's infancy. So how did this behemoth come to be? One theory suggests it's a fossil from the early universe, a relic of primordial density fluctuations frozen in time before inflation could smooth them out. Imagine the universe's first moments as a pot of boiling water, with bubbles of varying size. The Hercules-Corona Borealis Great Wall might be the ghost of one of those bubbles, a region where matter clumped together before expansion could dilute it. Others propose it's not a single structure at all, but a chance alignment of smaller clusters, a trick of cosmic pareidolia where our brains connect dots across the void. But even this explanation strains credulity. The statistical odds of such a perfect alignment are astronomically low. Then there's the radical possibility that our understanding of gravity is incomplete. Modified Newtonian dynamics, or MND, suggests gravity behaves differently at cosmic scales, allowing larger structures to form than standard models permit. But adopting MND would mean tossing out dark matter, a trade-off most physicists aren't ready to make. Alternatively, the wall might hint at exotic physics, remnants of a collision with another universe, or evidence that inflation wasn't as uniform as we thought. What makes this discovery so thrilling and humbling is what it represents. The Hercules-Corona Borealis Great Wall isn't just a curiosity, it's a cosmic roadblock forcing us to question whether we've misread the universe's blueprints. Every time we think we've grasped the limits of scale and structure, the cosmos throws another curveball, reminding us that the deepest mysteries aren't always in the distant past or the quantum foam. Sometimes they're hiding in plain sight, written across the sky in galaxies we've barely begun to map. And until we crack its code, this gargantuan wall stands as both a monument to our ignorance and a beacon calling us to look further. In the quiet depths of interstellar space, far beyond Pluto's frozen reach, two robotic pioneers were caught breaking the universe's speed limit, except they weren't speeding up. They were slowing down. NASA Pioneer 10 and 11 probes, launched in the 1970s to explore the outer solar system, became the center of one of modern astronomy's most perplexing puzzles when scientists noticed their trajectories were off by nearly 300 miles, not over days or weeks, but decades. An unseen force equivalent to a 10 billionth of a gravity on Earth was tugging them back toward the Sun. Dubbed the Pioneer Anomaly, this tiny deviation defied every known law of orbital mechanics. At first, engineers assumed it was a simple glitch, maybe residual fuel leaking from the probe's thrusters or a misaligned antenna radiating heat unevenly. But as years turned into decades and both spacecraft, now billions of miles apart, exhibited the exact same unaccounted deceleration, the anomaly grew harder to dismiss. By the late 90s, physicists had ruled out conventional explanations one by one. The probe's radioactive power sources, known to emit heat, became prime suspects. Perhaps infrared radiation pushing against the craft's dish-shaped antennas acted like a minuscule brake. Meticulous calculations suggested this could explain part of the drag, but bafflingly, not all of it. That's when the theories got wild. Some proposed the gravity of the solar system itself was subtly stronger than predicted, hinting at flaws in Einstein's general relativity. Others pointed to dark matter. Maybe the probes were plowing through invisible halos of the stuff, their momentum sapped by collisions with particles we can't detect. There were even whispers of entirely new physics, like modified gravity theories that only manifest over vast distances, but the most unsettling possibility: that we'd stumbled upon a local effect, something peculiar to the Pioneer's design, meaning the anomaly wasn't cosmic at all, but a quirk of human engineering. The mystery took a dramatic turn in 2012 when a team analyzing decades of telemetry finally cracked part of the code. Heat was the culprit, not just from the power sources, but from every electrical component on board. The probe's lopsided thermal radiation created a faint but constant recoil, like a car idling with one window open. Yet even this revelation left gaps. The math still didn't add up perfectly, leaving a whisper of unaccounted deceleration. Was it instrument error, an undiscovered systematic flaw, or something stranger? What makes the Pioneer anomaly so enduring isn't just the physics, it's the parable. Here were two machines built with 1970s technology, revealing a crack in our understanding so subtle it took 30 years to notice. It's a reminder that the universe doesn't always shout its secrets. Sometimes it murmurs them in the faintest of signals. And while most scientists now consider the case closed, that lingering discrepancy nags like an unsolved equation. Maybe the real lesson isn't about what slowed the Pioneers down, but how easily we might have missed the anomaly altogether had we not been paying exquisitely close attention. Hidden in the vast sea of microwave static that fills the cosmos, there's a cold spot so bizarre it makes astronomers question whether we're seeing a glitch in reality itself. This cosmic anomaly, known as the CMB cold spot, spans nearly 200 million light-years and registers as a chilling void in the otherwise uniform afterglow of the Big Bang. Temperatures here dip sharply, just a few millionths of a degree colder than their surroundings, but in the finely tuned symphony of the cosmic microwave background, that tiny dip screams like a wrong note. At first glance, it might seem like a statistical blip, a random fluctuation in the universe's thermal fingerprint, but the odds of such a pronounced cold spot appearing by chance. Less than 1 in 50, that's like rolling a die 100 times and never landing on 6 possible, but so unlikely it begs for another explanation. One theory suggests it's a supervoid, an enormous region of space where galaxies are strangely scarce, creating a pocket of lower energy. But here's the problem. Even the largest known voids can't account for the cold spot's extreme temperature drop. It's like expecting a gentle breeze to explain a hurricane. The math just doesn't add up. Then there's the multiverse hypothesis. Some physicists speculate the cold spot could be a bruise left by a collision with another universe during the inflationary era, a cosmic fender bender that left our reality dented. In this scenario, the spot would be a window into a parallel cosmos, its energy subtly draining into ours like heat seeping through a crack in a wall. It's a radical idea, but not without precedent. Theoretical models of bubble universes colliding predict signatures eerily similar to what we've observed. But perhaps the most unsettling possibility is that the cold spot is evidence of a cosmic defect, a relic from the universe's birth when spacetime itself might have knotted or torn. Just as ice crystals form cracks as they freeze, the rapid cooling of the early cosmos could have spawned topological flaws, regions where the fabric of reality is fundamentally twisted. These defects, predicted by some grand unified theories, would warp space around them, leaving behind telltale cold patches as their calling cards. What makes this mystery so compelling isn't just the wild theories, it's the data's stubborn refusal to fit neatly into any box. Every time we think we've pinned it down, the cold spot throws another curveball. New surveys with telescopes like the Atacama Cosmology Telescope keep refining our maps, yet the anomaly persists cool and enigmatic. Whether it's a statistical ghost, a multiverse bruise, or a cosmic knot, one thing's clear. The universe is still keeping secrets, and the cold spot is its most tantalizing whisper yet. Deep in the constellation Cancer, a planet orbits so close to its star that a single year lasts just 18 hours, and its surface is literally on fire. Welcome to 55 Cancri E, a world where the ground beneath your feet would be worth trillions if you could survive long enough to pick it up. Astronomers call it the Diamond Planet, but this isn't some glittering gem floating peacefully in space. It's a super-Earth forged in extremes, where unimaginable pressure cooks carbon into crystal while rivers of lava carve continents of solid diamond. Discovered in 2004, 55 Cancri E defies every expectation of what a planet can be. Roughly twice Earth's size but 8 times as massive, its density suggests an interior packed with crystalline carbon, the very stuff of diamonds. Picture this: beneath a scorching atmosphere of hydrogen and helium, a mantle hundreds of miles deep could be one gigantic diamond lattice, compressed so tightly it behaves more like metal than stone. If you could chip off a piece and somehow escape temperatures hot enough to melt iron, you'd be holding material purer than any jewel on Earth. But here's the twist: this cosmic treasure chest sits atop a nightmare landscape. With surface temperatures soaring above 4,000 degrees Fahrenheit, 55 Cancres dayside is a seething ocean of molten lava. Tidal forces from its sun keep the planet locked in a gravitational vise, one face perpetually scorched while the other simmers in eternal twilight. Some models suggest its crust might be paper-thin, fracturing constantly under the strain, leaking fresh lava that hardens into graphite only to sink back into the depths and recrystallize as diamond. It's a planet-sized pressure cooker, turning carbon into jewels through brute force. The real mystery: how such a world came to exist. Most carbon-rich planets form in systems where the primordial nebula was overflowing with heavy elements, but 55 Cancri star has less carbon than our Sun. One theory posits the planet was born farther out, where icy compounds could accumulate before migrating inward and shedding its lighter elements. Another suggests it might be the corpse of a gas giant, its hydrogen envelope stripped away by stellar winds, leaving behind a dense core of compressed carbon. Yet for all its violence, 55 Cancri offers a glimpse into the universe's alchemy. Under the right conditions, even something as mundane as carbon, the same element in your pencil lead, can transform into celestial royalty. And if this glittering hellscape exists, how many other diamond worlds lurk in the cosmos? Planets where sapphires rain from metallic clouds, or entire mountain ranges gleam with rubies. The universe, it seems, has a flair for the extravagant, crafting jewels on scales we're only beginning to imagine. In the quiet static of radio telescope data, where scientists usually hunt for faint galaxies or the whispers of cosmic dawn, researchers recently stumbled upon something that made them do a double-take: enormous, perfect rings of radio light hanging in space like celestial smoke rings. They're called odd radio circles, or ORC, and they're so bizarre that when first discovered in 2020, astronomers literally wrote in their paper, "There is no obvious known counterpart or origin." Translation: we've never seen anything like this before. What makes ORCs so baffling isn't just their shape, though their near-perfect circular symmetry is odd enough. It's their scale. These rings span hundreds of thousands of light-years, dwarfing entire galaxies. Yet despite their immense size, they're invisible in optical, infrared, or X-ray light. Only radio telescopes can see them, as if they're cosmic holograms projected in a frequency only machines can decode. Even stranger, most ORCs float in isolation, far from the dense galaxy clusters where dramatic cosmic events usually unfold. It's like finding a hurricane spinning calmly in the middle of a desert, a phenomenon with no business being where it is. The plot thickens with how they were found. Unlike traditional discoveries made by astronomers squinting at telescope images, ORCs were first flagged by an AI sifting through data from Australia's ASCAP radio telescope array. The algorithm spotted these faint rings hidden in the noise, their perfectly circular forms standing out like fingerprints on glass. But when scientists rushed to confirm them with other telescopes, they hit another wall. No known astrophysical process, supernova, black hole jets, galactic collisions, could explain rings this large, this symmetrical, and this invisible to every other wavelength. One leading theory suggests ORCs might be the shock waves of gargantuan explosions, perhaps triggered by supermassive black holes belching out energy in titanic bursts. Picture a pebble dropped in a pond, sending ripples outward. Except the pond is intergalactic space, and the pebble is a black hole eruption powerful enough to ripple across hundreds of thousands of light years. Another idea posits they're the aftermath of a starburst tsunami. where a galaxy unleashes such a ferocious wave of star formation that the resulting stellar winds blow a bubble in the surrounding gas. But even these explanations struggle to account for Orc's pristine symmetry, or why we don't see any optical traces of the fireworks that supposedly created them. Then there's the wild card. Could ORCs be evidence of something entirely new? Some theorists speculate they might be the imprint of wormholes, their gravitational lensing warping background radio light into rings. Others joke half-seriously about alien megastructures, though the sheer energy required to produce such signals would dwarf the output of entire civilizations. The most tantalizing possibility, that ORCs are the fingerprints of dark matter interactions, their radio glow betraying the presence of invisible particles colliding in ways we've yet to understand. What makes these ghostly rings so thrilling isn't just their mystery, it's what they represent. In an era where we've mapped millions of galaxies and traced the cosmic web itself, ORCs are a stark reminder that the universe still holds surprises hiding in plain sight. Every new observation peels back another layer, revealing not just gaps in our knowledge, but entire chasms we didn't know existed. And as radio telescopes grow more sensitive, one thing's certain: the more we look, the more these enigmatic circles seem to be whispering that the cosmos is far stranger than we ever dreamed. For decades, cosmologists have faced a cosmic accounting error so glaring it would make any auditor panic. Nearly half the universe's ordinary matter, the protons and neutrons that make up stars, planets, and us, has gone missing. Not dark matter, not exotic particles, but the same familiar atoms we're made of. The math is undeniable. According to the cosmic microwave background and Big Bang nucleosynthesis, baryonic matter should account for about 5% of the universe's total mass energy. But when astronomers tally up all the visible galaxies, stars, and gas clouds, they come up shockingly short. Where's the rest? This is the case of the missing baryons, and the trail leads to some of the most elusive structures in existence. The prime suspects: vast, diffuse rivers of superheated gas weaving between galaxies like cosmic spider silk. Known as the warm-hot intergalactic medium, or WIM, this plasma is so thin it's practically invisible, heated to millions of degrees, but spread so thinly that a cubic meter might contain just a single atom. Spotting it requires ingenious detective work. Astronomers use distant quasars as cosmic flashlights, analyzing how their light dims as it passes through these filaments. Specific absorption lines in the ultraviolet and X-ray spectra betray the presence of oxygen atoms stripped of electrons, floating in these scalding intergalactic currents. It's like tracking a ghost by the faint warmth it leaves on a doorknob. But even the WIM doesn't fully balance the books. Some matter hides even deeper in the shadows. Another clue emerged when researchers studied the Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background caused by hot gas scattering photons. By mapping these distortions around galaxy clusters, they found halos of million-degree gas extending far beyond what optical telescopes see. Meanwhile, advanced simulations suggest cosmic filaments should act as particle accelerators, generating faint radio emissions as electrons spiral along magnetic field lines. In 2020, the LOFAR radio telescope may have glimpsed this very signal, a faint glow tracing the bones of the cosmic web itself. The hunt takes stranger turns underground. Some theorize a fraction of missing baryons could be locked in primordial black holes, relics of the Big Bang too small to detect. Others propose exotic states like dark atoms, where protons and neutrons bind with hypothetical particles, rendering them invisible to our instruments. But the most promising leads still point to the WIM most extreme environments, regions where galaxies collide, superheating gas to temperatures that emit detectable X-rays. ESA's Athena X-ray Observatory, launching in the 2030s, aims to finally map these hidden reservoirs. Why does this matter? Because every atom unaccounted for is a gap in our understanding of cosmic evolution. These missing baryons are the mortar holding the large-scale structure of the universe together, the scaffolding upon which galaxies are built. Their discovery wouldn't just solve a puzzle, it would rewrite the story of how ordinary matter, from the tiniest dust grain to the grandest supercluster, came to be. And until we find them, our cosmic ledger remains embarrassingly unbalanced, a reminder that even the stuff we're made of can vanish before our eyes. Most dying stars leave behind chaotic, swirling clouds, a final gasp of gas and dust hurled into space in their death throes. But in the constellation Monoceros, 700 light-years away, one star didn't just die, it erupted in perfect geometry. The Red Rectangle Nebula, named for its bizarre crimson-hued, boxy shape, is one of the most symmetrical objects ever discovered in space. And at its heart, an X-shaped structure gleams like a cosmic crosshair, defying every expectation of how planetary nebulae should behave. This isn't just another pretty space cloud. The red rectangle's sharp angles and vivid rungs of dust look more like a stained glass window than a stellar explosion. Its central star, HD 44179, is a so-called post-HB star, an aging sun-like star that's expelled its outer layers but hasn't yet collapsed into a white dwarf. Normally, such stars produce round or spiral nebulae as they shed material evenly into space. So how did this one craft something so precise it looks engineered? The leading theory points to an unseen dance partner, a binary star. If HD 44179 has a companion, their orbital waltz could funnel ejected gas into twin cones, their interaction sculpting the X shape we see. Imagine two sprinklers spinning around each other, their water jets colliding to form an intricate pattern in midair. Similarly, stellar winds from both stars might have carved this nebula's extraordinary geometry over millennia. Infrared observations reveal a vast disk of dust around the central stars, likely the canvas upon which this cosmic artwork was painted. But there's a twist. Some researchers argue the X might not be shaped by stars at all, but by high-speed jets punching through the nebula's waste. These jets, possibly launched by magnetic fields or accretion processes, could act like cosmic cookie cutters, stamping out the nebula's sharp edges. Others propose the red rectangle symmetry comes from shock diamonds, stacked rings of gas formed as material slams into interstellar space at precise intervals, like ripples frozen in time. What makes this nebula truly mesmerizing isn't just its shape, it's the color. The deep red hue comes from a rare form of carbon-based molecules called polycyclic aromatic hydrocarbons, fluorescing under the central star's ultraviolet light. These molecules, common in soot and engine exhaust on Earth, are scattered across space, but nowhere are they as concentrated or as vividly illuminated as here. It's as if the dying star set its own funeral pyre ablaze with chemical artistry. The red rectangle challenges our assumptions about stellar deaths. Most models predict chaos asymmetric explosions, turbulent clouds. Yet this nebula whispers that under the right conditions, the universe can craft precision as fine as any watchmaker's. Whether its form comes from binary choreography, magnetic sculpting, or some undiscovered physics, one thing's certain. When this star chose its final act, it went out not with a bang but with a masterpiece. The moon has always been Earth's silent companion, a barren rock floating in the void, or so we thought. But when Apollo astronauts brought back lunar rocks in the late 1960s and early 70s, scientists made a startling discovery. These ancient samples contain tiny magnetic imprints, frozen evidence that the moon once had its own magnetic field. Here's the puzzle. Magnetic fields are usually generated by churning molten metal in a planet's core, a process called a dynamo effect. But the moon's core is small and sluggish, far too weak to power the kind of magnetic shield these rocks suggest. So how did our cosmic neighbor, just 1% of Earth's mass, pull off such a cosmic magic trick? One theory points to a lunar youth far more turbulent than we ever imagined. In its early days, the Moon may have spun much faster, its core stirred by the gravitational tug of war with Earth. Picture a dynamo powered not just by heat, but by motion, like a child spinning in a swivel chair, building momentum until everything blurs. Computer simulations show that if the Moon's orbit was closer and its rotation quicker, even its modest core could have generated a temporary magnetic field. But there's a catch. This short-lived dynamo would have faded as the Moon's rotation slowed, leaving behind only those magnetic whispers in the rocks. Then there's the impact hypothesis. The Moon's surface is pockmarked with colossal craters, relics of asteroid strikes that reshaped its history. Some researchers argue these collisions didn't just scar the surface, they might have jump-started the core. When a massive object slams into the Moon, the shockwaves could have sent ripples through its interior, stirring the molten metal like a spoon in a cup of coffee. These violent jolts might have triggered brief but intense magnetic bursts, imprinting the rocks during moments of cosmic chaos. It's a tantalizing idea, but one that raises new questions. Why do some rocks show magnetic signatures lasting millions of years, while others flicker like a candle in the wind? The most radical explanation: the Moon's mantle itself might have played a role. Certain minerals, when heated and pressurized, can become electrically conductive. If the early Moon's mantle was rich in these materials, convection currents could have generated electric currents, weaving a magnetic web without relying on the core at all. It's like discovering a flashlight powered not by batteries, but by the heat of your hand, a clever workaround that rewrites the rules. What makes this mystery so profound isn't just the Moon's past, but what it reveals about other worlds. If a small, geologically quiet body like the Moon once held a magnetic field, what does that mean for asteroids, exoplanets, or even moons orbiting Jupiter and Saturn? Magnetic fields shield surfaces from deadly solar radiation, creating safe havens for potential life. The Moon's hidden history suggests these protective bubbles might be more common and more fleeting than we ever guessed. Every rock brought back from the Moon is a time capsule, holding secrets from an era when our closest neighbor was a dynamic, evolving world. Those faint magnetic traces are more than scientific curiosities. They're clues to a lunar adolescence full of fire and motion, a far cry from the silent sentinel we see today. And as we prepare to return to the Moon with new missions and tools, one thing's certain: the more we learn, the less we realize we know. Picture the universe as a balloon slowly inflating, with galaxies drawn like dots on its surface. Now imagine that balloon suddenly starts expanding faster and faster, as if some unseen force is pumping it with extra air. That's the reality astronomers faced in the late 1990s when two separate teams made a discovery so shocking it upended cosmology. The universe isn't just expanding, it's accelerating. And whatever's causing this cosmic speed-up has a name that sounds straight out of a sci-fi novel: dark energy. This revelation was a sucker punch to physics. Gravity, the force that binds planets, stars, and galaxies together, should be slowing the expansion, not revving it up. Imagine tossing a ball in the air, only to watch it shoot away faster instead of falling back. That's the level of absurdity dark energy introduced. The teams studying distant supernova expected to measure a deceleration, a cosmic drag from gravity's pull. Instead, they found the opposite. The universe's expansion is hitting the gas pedal, and no one knows why. So what could possibly overpower gravity on such a colossal scale? The leading candidate is Einstein's cosmological constant, a repulsive energy woven into the fabric of space itself. Einstein originally proposed it to keep the universe static, later calling it his greatest blunder when Hubble proved expansion. But now it's back with a vengeance, potentially explaining dark energy as a property of empty space. Here's the twist: quantum physics predicts the vacuum of space should fizz with energy, but calculations overshoot the observed value by a factor of 10 to the power of 120. That's like predicting a candle's glow and getting the output of the sun, a discrepancy so vast it suggests we're missing something fundamental. Then there's quintessence, a dynamic field that changes over time, unlike the static cosmological constant. Named after the fifth element of ancient philosophy, this hypothetical substance could behave like an anti-gravity fluid, thinning or thickening as the universe evolves. Some models even suggest it might eventually flip, turning repulsive today but attractive tomorrow, a cosmic pendulum that could one day halt acceleration and trigger a big crunch. But without direct evidence, quintessence remains a ghost in the equations. The stakes couldn't be higher. Dark energy makes up 68% of the universe's energy budget, dictating its ultimate fate. Will expansion tear galaxies apart in a big rip, or will dark energy fade, leaving the cosmos to coast into cold darkness? Current data favors endless acceleration, but anomalies linger. Recent measurements of the Hubble constant the rate of expansion disagree depending on whether we use near-by supernova or the cosmic microwave background. This Hubble tension might hint at dark energy's nature changing over cosmic time, or worse, flaws in our standard model of cosmology. What makes this enigma so thrilling isn't just the mystery, it's the irony. After centuries of mapping stars and galaxies, we've learned that the universe is dominated by something invisible, intangible, and utterly alien to our experience. Dark energy doesn't just defy gravity. It defies intuition, pressing us to question whether we've misunderstood space, time, or the very laws of physics. And until we crack its code, every observation, every telescope, every theory is a step toward answering the most profound question of all. What exactly is the universe made of, and where is it rushing to so fast? When the James Webb Space Telescope peered back over 13 billion years into the universe's infancy, it didn't just spot ancient galaxies, it found cosmic giants that shouldn't exist. These primordial behemoths, some weighing in at over 100 billion suns, challenge every assumption about how quickly the early cosmos could assemble such colossal structures. According to our best models, these galaxies shouldn't have had enough time to grow so massive so soon after the Big Bang. It's like digging up a fossil of a fully grown T-Rex in a layer of sediment meant to hold only single-celled organisms, an impossible relic that threatens to rewrite history. The heart of the problem lies in the cosmic timeline. Current theories suggest that after the Big Bang, the universe spent its first few 100 million years in a murky, dark ages, where hydrogen gas slowly pooled under gravity's pull, eventually igniting the first stars. Small protogalaxies should have taken billions of years to merge and mature into the spirals and ellipticals we see today. Yet JWST infrared eyes revealed galaxies like Glass Z13, a monster already in place when the universe was just 300 million years old, far too soon for gravity alone to work its magic. One explanation: these galaxies might have formed from seeds of ultra-concentrated dark matter, collapsing into stars at breakneck speed. But even that theory strains credibility, requiring densities of dark matter so extreme they border on the fantastical. Then there's the question of light. These early galaxies aren't just massive, they're blindingly bright, churning out stars at rates that dwarf modern galaxies. Take Macy's Galaxy, another JWST discovery. It's forming stars 20 times faster than the Milky Way despite being a fraction of its age. Some astronomers argue this hyper-efficiency might come from pristine gas clouds, unpolluted by heavy elements, collapsing more easily into stars. Others propose a radical idea. What if the first stars weren't just bigger but fundamentally different? Population 3 stars, a hypothetical generation of supermassive, short-lived giants, could have seeded these galaxies with rapid bursts of star formation before vanishing without a trace. The implications are staggering. If these galaxies are real, not artifacts of lensing or measurement errors, they could upend our understanding of cosmic dawn. Maybe dark energy played a role in accelerating structure formation, or perhaps inflation. The universe's exponential expansion post-Big Bang didn't unfold quite as smoothly as we thought. There's even chatter about entirely new physics, like modifications to gravity or exotic dark matter interactions that turbocharged galaxy growth, but the most tantalizing possibility: that we've misjudged time itself. What if the universe is older than we think, giving these galaxies extra eons to mature? It's a controversial notion, clashing with the pristine chronometry of the cosmic microwave background. Yet as JWST uncovers more of these cosmic anomalies, astronomers are left with a haunting question. Are we witnessing the limits of our models, or the first clues to a universe far stranger than we ever imagined? Every new observation is a step closer to the answer, and a reminder that the cosmos loves to defy the rules we set for it. At Saturn's North Pole, a storm rages that defies every law of atmospheric physics. We understand not a swirling vortex like Earth's hurricanes, but a near-perfect hexagon, wider than our entire planet, with sides longer than the distance from New York to London. This six-sided behemoth was first spotted by Voyager in the 1980s, and when Cassini arrived decades later, it was still there, unchanged, as if someone had etched a geometric tattoo into the gas giant's atmosphere. The strangest part: storms don't behave like this. They don't form razor-sharp angles or maintain precise symmetry for 40 years. On Earth, even the most powerful hurricanes dissolve into chaos within weeks. Yet Saturn's hexagon persists, a cosmic anomaly spinning at its own enigmatic rhythm. To grasp just how bizarre this is, picture trying to stir honey into your tea and having it spontaneously arrange itself into a hexagon. Earth's weather systems are messy, dynamic, and short-lived because our atmosphere is thin, turbulent, and heated unevenly by the sun. But Saturn, its atmosphere is a deep, roiling sea of hydrogen and helium, with winds screaming at 320 miles per hour speeds that should shred any structure into oblivion. So how does this polygon of storms stay intact? Laboratory experiments might hold a clue. When scientists spin a tank of fluid at different speeds, they can create polygonal shapes, squares, triangles, even octagons, mimicking what we see on Saturn. The key seems to be shear forces, layers of gas moving at varying velocities, creating stable waves that lock in the hexagon's edges. It's like nature's own version of a spinning coin, where centrifugal force and friction conspire to form temporary order. Yet even this explanation feels incomplete. Why 6 sides? Why not 8 or 4? Some theorists point to Saturn's deep internal structure, suggesting the hexagon might be the visible tip of a gargantuan, planet-sized jet stream rooted thousands of miles below the clouds. Others propose it's a standing wave, akin to the vibrations that make a guitar string hum at specific frequencies, except scaled up to planetary dimensions. Then there's the wild card, electromagnetism. Saturn's powerful magnetic field could be interacting with charged particles in its atmosphere, sculpting the storm into this precise geometry. But without direct measurements beneath those thick clouds, we're left guessing. The hexagon's endurance is just as puzzling as its shape. Earth's longest-lived storms, like Jupiter's Great Red Spot, eventually fade or change form. But Saturn's hexagon has outlasted every spacecraft sent to study it. Could it be replenished by some hidden energy source deep within the planet? Or is it a self-reinforcing system where the very forces that sustain it also prevent its collapse? Every time we think we've pinned it down, the hexagon throws another curveball, like the discovery of towering 100-mile-high walls of cloud along its edges, or the way its central hurricane pulses with mysterious heat. What makes this storm so captivating isn't just the science, it's the symbolism. Here's a structure that shouldn't exist, yet it spins on, indifferent to our models and expectations. It's a reminder that the universe has a flair for the unexpected, crafting order from chaos in ways we're only beginning to comprehend. and until we send another probe to Saturn's swirling north, the Hexagon will remain one of the solar system's most elegant enigmas, a cosmic snowflake stamped onto a gas giant, whispering secrets we've yet to decode. Just when astronomers thought they'd seen the strangest star in the cosmos, along came VVVWIT-08, a celestial enigma that made Tabby's star look positively ordinary. Located 25,000 light-years away in the constellation Sagittarius, this unassuming pinpoint of light did something that defied all expectations. It nearly blinked out entirely, dimming by an astonishing 97% before slowly brightening again over months. To put that in perspective, even the most dramatic known eclipsing binary stars only fade by about 60%. This wasn't a gentle dip, it was as if someone had thrown a cosmic dimmer switch, leaving astronomers scrambling for explanations that ranged from the plausible to the downright apocalyptic. At first glance, the natural explanation seems obvious. Dust, thick clouds of cosmic debris orbiting the star could theoretically block its light, but here's where things get weird. For dust to cause such an extreme dimming event, the cloud would need to be impossibly dense, far thicker than any known protoplanetary disk. Worse still, follow-up observations revealed the dimming wasn't symmetric. Instead of a clean, U-shaped light curve typical of transiting objects, VVVWIT-08 dimming had jagged, irregular edges, as if whatever was blocking it had a bizarre, fragmented structure. Some researchers proposed a swarm of shattered comets or asteroids, their debris field twisted into odd shapes by a nearby planet's gravity. Others pointed to warped accretion disks from a companion black hole or neutron star, bending light in ways we don't fully understand. Then there's the timing. Unlike Tabby's star's unpredictable flickers, VVVWIT-08 dimmed with eerie regularity roughly once every few decades, suggesting whatever caused it might be on an orbital schedule. This cyclical nature rules out one-off catastrophes like planetary collisions, pointing instead to a recurring phenomenon. One team calculated that a single, massive object with a 75-year orbit could explain the pattern, perhaps a brown dwarf dragging a retinue of dust clouds in its wake. But again, the numbers strain credibility. The dust required would outweigh Jupiter by a factor of 10, making it more of a failed star than a simple debris field. Of course, no discussion of extreme stellar dimming would be complete without the elephant in the room: alien megastructures. The 97% dimming threshold is particularly tantalizing because it aligns suspiciously well with theoretical models of Dyson swarms, hypothetical arrays of energy collecting satellites an advanced civilization might build around a star. Unlike Tabby's star's partial dimming, which could be explained by natural phenomena, VVVWIT-08 near total blackout is exactly what you'd expect if a civilization were in the late stages of enclosing their sun. The irregular light curve could reflect construction zones of varying density, while the cyclical nature might indicate planned phases of development. But before we book tickets to Sagittarius, let's pump the brakes. The universe has a long history of serving up mysteries that initially seemed artificial, from pulsars mistaken for alien beacons to quasars dismissed as local radio interference. What makes VVVWIT-08 so compelling isn't just the extreme dimming, but the fact that it challenges our definitions of what's possible. Whether it's a previously unknown type of variable star, a gravitational lensing effect we've yet to model, or something even stranger, this cosmic flashbulb forces us to confront how much we still don't understand about stellar behavior. Perhaps the most telling clue lies in the name itself. WIT stands for "What is this?", a playful admission that sometimes the universe throws curveballs that leave even the sharpest minds scratching their heads. As new telescopes like the Vera C. Rubin Observatory come online, we may finally get answers. Until then, VVVWIT-08 remains a perfect storm of mystery, a celestial Rorschach test where every observer sees something different, a dust cloud, a construction site, or a cosmic signpost pointing toward discoveries we can't yet imagine. Imagine measuring the same room with two different rulers only to find each one gives you a wildly different answer. That's exactly the headache plaguing cosmologists today, except the room is the entire observable universe and the rulers are our most trusted tools for measuring cosmic expansion. Welcome to the Hubble tension, a full-blown crisis in modern astronomy where the universe's expansion rate. The Hubble constant refuses to give us a consistent answer. Depending on how you measure it, the numbers disagree by just enough to keep scientists up at night, whispering the forbidden question: what if our entire understanding of physics is missing a piece? The roots of this conflict trace back to two competing methods. The first, known as the local ladder, relies on nearby cosmic landmarks, especially Cepheid variable stars, the universe's natural lighthouses. These stars pulse at rates directly tied to their true brightness, letting astronomers calculate distances with remarkable precision. By measuring Cepheids in galaxies close to ours, then tracking how those galaxies move away from us thanks to redshift, we get an expansion rate of roughly 73 kilometers per second per megaparsec. That means for every additional megaparsec of distance, about 3.3 million light-years, space itself stretches faster by 73 kilometers every second. Simple, right, except when we look at the cosmic microwave background, the afterglow of the Big Bang, the story changes. The Planck satellite's exquisitely detailed maps of this ancient light let physicists calculate the Hubble constant based on the universe's infancy, factoring in dark matter, dark energy, and the whole cosmic recipe. But here's the twist. Planck's number is 67 kilometers per second per megaparsec, nearly 10% lower than the Cepheid-based result. At first, astronomers brushed it off as a calibration error. But after years of cross-checking using everything from supernova to gravitational waves, the gap refuses to close. So what's really going on? One possibility is that we've misjudged something basic, like the behavior of Cepheids or the properties of cosmic dust skewing our measurements. But the more thrilling option, that we're seeing fingerprints of undiscovered physics. Maybe dark energy isn't constant but evolves over time, subtly tweaking the expansion rate. Or perhaps dark matter interacts with itself in ways we haven't accounted for, warping large-scale structure. There's even speculation about an early dark energy phase that briefly turbocharged the universe's youth, leaving a discrepancy baked into our modern measurements. The implications are staggering. If the Hubble tension is real, not just a measurement fluke, it could mean our standard model of cosmology needs a rewrite. After all, these aren't just numbers on a spreadsheet. They're the foundation for everything from the age of the universe to the fate of galaxies. Right now, telescopes like JWST are diving into the dispute, scrutinizing Cepheids and ancient galaxies with unprecedented clarity. With every new data point, we edge closer to an answer. Will the tension snap, revealing a universe stranger than we dreamed, or will it dissolve into the humdrum of systematic error? One thing's certain, the cosmos loves a good plot twist, and this one's far from over. There's a reason neutrinos are called ghost particles. They pass through entire planets like they're not even there, leaving barely a trace. Trillions stream through your body every second, and you'd never know it. But in 2022, scientists pulled off the impossible. They caught a handful of these phantoms red-handed, tracing them back to a cosmic powerhouse called NGC 1068, a nearby galaxy with a supermassive black hole devouring matter at its core. This wasn't just a scientific first, it was a glimpse into a new era of astronomy, where invisible messengers reveal secrets light alone cannot. NGC 1068, also known as Messier 77, is no ordinary galaxy. At 47 million light-years away, it's one of the closest active galactic nuclei, or AN, a term for galaxies whose central black holes are actively feeding, spewing radiation across the universe. But what made this discovery groundbreaking wasn't the light pouring from its core. It was the neutrinos. Using the Ice Cube Observatory, a colossal detector buried deep in Antarctic ice, physicists identified 79 high-energy neutrinos originating from the galaxy's heart. Unlike light, which can be scattered or absorbed, neutrinos travel unimpeded, carrying information straight from the universe's most violent environments. Why does this matter? Because neutrinos are the ultimate cosmic witnesses. Light gives us snapshots of the universe's surface, but neutrinos, uncharged, nearly massless, and barely interacting with matter, come straight from the engine room. In the case of NGC 1068, they're likely born in the maelstrom around its black hole, where particles are accelerated to near light speed, colliding violently to produce these elusive ghosts. Spotting them confirms a long-held suspicion. AGNs are cosmic particle accelerators, capable of generating neutrinos with energies dwarfing anything our most powerful colliders can produce. This discovery is also reshaping multi-messenger astronomy, a field that combines signals from light, gravitational waves, and now neutrinos to paint a fuller picture of the cosmos. Imagine investigating a crime scene with only a blurry photo, then suddenly getting audio recordings and fingerprints. That's the power of neutrinos. They help us probe regions too dense for light to escape, like the inner disks of black holes where gravity twists space into knots. Already, researchers are using these particles to test theories about how AGNs influence galaxy evolution, seed the universe with high-energy radiation, and even contribute to the mysterious cosmic rays that bombard Earth. But here's the twist. NGC 1068's neutrinos shouldn't be this energetic. Current models struggle to explain how the galaxy's black hole, a relatively modest feeder compared to quasars, can produce particles with such staggering force. Some theorists propose hidden mechanisms like magnetic reconnection events or shock waves in the accretion disk, supercharging the neutrinos. Others wonder if we're seeing a new class of AGN altogether, one where black holes unleash energy in ways we've never witnessed. The hunt for answers is just beginning. Upgraded detectors like Ice Cube Gen 2 and the upcoming KM3 NET in the Mediterranean aim to catch more of these spectral messengers, mapping their origins across the sky. With every new neutrino traced back to a galaxy, we're stitching together a hidden map of the universe, one written not in light, but in the faintest whispers of particles that barely acknowledge the existence of matter. And as the data rolls in, one thing becomes clear: the ghosts are talking. We're finally learning how to listen. In the quiet constellation of Gemini, hidden among the familiar sparkle of the Milky Way, lurks a cosmic paradox, a black hole so massive it defies the very laws that should govern its existence. Known as LB1, this gravitational behemoth weighs in at a staggering 70 times the mass of our Sun, a figure that sent shockwaves through the astrophysics community when it was discovered in 2019. According to everything we know about stellar evolution, black holes born from collapsing stars shouldn't get this big. So what exactly are we looking at? A cosmic glitch, a merger remnant, or something entirely new lurking in the shadows of our galaxy? The problem starts with something called the pair instability limit. When massive stars, we're talking 30 to 40 solar masses, reach the end of their lives, they don't just collapse quietly into black holes. Instead, their cores become so hot that photons spontaneously convert into electron-positron pairs, robbing the star of the outward pressure needed to resist collapse. The result, a runaway thermonuclear explosion so violent it obliterates the star completely, leaving nothing behind, no black hole, no remnant, just stardust scattered across the cosmos. This process should cap stellar black holes at around 50 solar masses, making LB1 70 solar mass bulk a glaring anomaly. One explanation is that LB1 wasn't born from a single star's death, but from a dance of destruction between two smaller black holes. Imagine two heavyweight champions merging in the cosmic ring, their combined mass breaking the scales. We know such mergers happen. LIGO gravitational wave detectors have caught plenty of them, but there's a catch. LB1's companion star, a blazing B-type giant, orbits it in a near-perfect circle, with none of the telltale wobbles or distortions you'd expect if a violent merger had recently occurred. It's like finding a pristine dinner plate next to a demolished building the pieces don't quite fit. Then there's the dark horse theory. Maybe we've underestimated how massive stars can grow in the first place. Some astronomers argue that in metal-poor environments, regions where elements heavier than hydrogen and helium are scarce, stars might avoid the pair instability trap, growing to monstrous sizes before collapse. LB1's host star fits this profile, its composition hinting at ancient origins in a primordial gas cloud. If true, it would mean the universe's first stellar black holes could have been far heftier than we ever imagined, lurking unnoticed in our cosmic backyard. Of course, not everyone's convinced. Skeptics point to alternative explanations, like a chance alignment mimicking a black hole's gravitational pull, or even exotic phenomena like boson stars, theoretical objects made of ultra-light particles that could masquerade as black holes under certain conditions. But the more we study LB1, the stranger it gets. Recent spectroscopy reveals its accretion disk, the swirling maelstrom of gas feeding the black hole, glows with unexpected patterns, suggesting magnetic fields or turbulence unlike anything seen in smaller black holes. What makes this discovery so thrilling isn't just the mystery, it's what it reveals about the gaps in our cosmic playbook. LB1 forces us to confront an uncomfortable truth. Black holes, those seemingly simple gravity wells, might come in flavors we haven't even dreamed of. Whether it's a merger survivor, a relic from the universe's early days, or something entirely uncharted, one thing's certain: the Milky Way just got a lot more interesting. And as telescopes grow sharper and models more refined, we're left with a tantalizing question. If LB1 breaks the rules, how many others are out there waiting to be found? Stars don't just vanish, they go out with a bang, a supernova so bright it can outshine entire galaxies. But in 2015, astronomers stared at Hubble Space Telescope images of a distant galaxy and realized something was terribly wrong. A massive star 25 times heavier than our Sun had simply disappeared. No explosion, no lingering nebula, just an eerie absence where a luminous giant once blazed. Dubbed N6941, this cosmic ghost became the first confirmed failed supernova, a star that skipped its own funeral and left scientists scrambling to rewrite the rules of stellar death. What makes this case so unsettling is how thoroughly it defies expectations. Stars this massive are supposed to die spectacularly, their cores collapsing into neutron stars or black holes while their outer layers detonate in a fireball visible across the universe. But N6914 didn't follow the script. One year, Hubble spotted it shining brightly. The next, only a faint infrared glow remained, as if the star had imploded quietly into a black hole without the usual fireworks. It's the cosmic equivalent of watching a building vanish overnight, leaving no rubble, no sound, just an empty lot where a skyscraper should be. So how does a star cheat death so dramatically? The leading theory involves something called a massive fail. If a star's core collapses fast enough, the resulting black hole might swallow all the outgoing shockwaves that would normally trigger a supernova. Picture a sinkhole opening beneath a fireworks factory. The entire structure gets sucked underground before the explosives can detonate. In this scenario, the star's outer layers would drain straight into the black hole's maw, leaving no trace beyond a wisp of heat. It's a stellar disappearing act so clean it leaves astronomers questioning how often we've missed these events in the past. But there's a twist. Some models suggest these unnova might actually be more common than we think. Stars in the 20 to 40 solar mass range could be especially prone to quiet collapses, their fates hidden by cosmic dust or overlooked in crowded galactic neighborhoods. Recent surveys using advanced infrared telescopes have flagged dozens of similar candidate stars that flicker and fade without the fanfare of a supernova. If confirmed, it would mean we've been undercounting black hole births by a staggering margin, missing entire generations of stellar corpses lurking in the shadows. The implications ripple far beyond one strange star. Failed supernova could explain why we've struggled to match the number of observed supernova with the rate of black hole formation. They might also shed light on the origins of heavy elements. If too many stars skip the explosion phase, where does the universe's gold, platinum, and uranium really come from? Even gravitational wave astronomy feels the reverberation's quiet collapses could produce black hole mergers with unique mass distributions, subtly altering the signals LIGO detects. N6914's silent exit isn't just a curiosity, it's a cosmic wake-up call. For every star that dies loud enough for us to notice, there might be another slipping away unseen, rewriting its own ending in the dark. And as telescopes grow more sensitive to these infrared ghosts, one thing becomes clear: the universe has more ways to kill a star than we ever dreamed. Rising like titanic hourglasses from the heart of our galaxy, two colossal orbs of gamma-ray light stretch 25,000 light-years into the void, one reaching north, the other south, their perfect symmetry defying the chaos of the Milky Way's core. These are the Fermi bubbles, first spotted in 2010 when astronomers sifting through data from NASA's Fermi Gamma-Ray Space Telescope noticed an eerie glow that shouldn't have been there. Not random speckles of radiation, but crisp, matching structures towering above the galactic plane, their edges razor-sharp as if cut with cosmic scissors. What could possibly blast such enormous, identical formations out of a supermassive black hole's chaotic neighborhood? The scale alone is staggering. Each bubble spans half the visible diameter of our galaxy, packed with particles moving near light speed, emitting gamma rays like cosmic lighthouses. Their energy output rivals 100,000 supernovae, yet there's no record of such cataclysms in our galactic history. The leading theory points to Sagittarius A, the Milky Way's supermassive black hole, as the architect. Sometime in the last few million years, it might have gorged on an unusually large meal, perhaps a wayward gas cloud or a star torn apart by tidal forces, triggering a brief but furious outburst of energy. Jets of relativistic particles, normally constrained to narrow beams, could have inflated these bubbles like balloons, their symmetrical path shaped by the black hole's spin and the galaxy's magnetic field. But there's a twist. Some astronomers argue the bubbles might not be the work of Sagittarius at all. Alternative models suggest a starburst frenzy, where a sudden burst of star formation near the galactic center sent shockwaves rippling outward, accelerating particles to extreme energies. Observations from the E-Rosetta X-ray telescope even reveal faint, matching X-ray structures nested within the Fermi bubbles, hinting at multiple violent events layered like rings in a tree trunk. Could the Milky Way have endured not one but several eruptions, each leaving its mark on these ghostly remnants? The real enigma is their symmetry. Cosmic explosions are rarely so perfectly balanced. Supernova remnants and active galactic nuclei jets typically show lopsided, messy structures. Yet the Fermi bubbles stand with eerie precision, their shapes preserved for millions of years despite the galaxy's turbulent environment. One possibility is that the galactic halo, a diffuse cloud of hot gas surrounding the Milky Way, acted like a mold, channeling the outflow into uniform lobes. Others speculate that dark matter's gravitational influence somehow stabilized the bubble's growth, though this remains wildly speculative. What's clear is that these structures are more than ancient relics. They're a live wire into the galaxy's explosive past. Recent studies suggest the bubbles might still be growing, their edges crackling with newly accelerated particles. And if similar structures exist around other galaxies hidden in plain sight, waiting for telescopes sensitive enough to spot them, they could rewrite our understanding of how often black holes wake from their slumber. The Fermi bubbles aren't just a mystery, they're a time capsule preserving the echoes of a time when the Milky Way's calm spiral mask slipped, revealing the monster lurking at its heart. And as gamma-ray telescopes grow sharper, we may soon learn whether these giants are one of a kind, or just the first of many cosmic matryoshka dolls waiting to be opened. Imagine a galaxy so wispy, so faint, it barely clings to existence, a cosmic ghost where stars drift apart like fireflies in an endless night. This isn't science fiction, it's the reality of the Dragonfly 44 galaxy, a celestial oddity that rewrites everything we thought we knew about how galaxies survive. Discovered in 2015 by the Dragonfly Telephoto Array, a telescope literally designed to spot the invisible, this ultra-diffuse galaxy defies logic. Spanning as wide as the Milky Way but glowing 1,000 times dimmer, Dragonfly 44 is so transparent you could stare right through it and barely notice. Yet the real shock wasn't its faintness, it was the revelation that this ghostly giant somehow exists without dark matter, the invisible glue that supposedly holds all galaxies together. Dark matter isn't just a minor ingredient in the cosmic recipe, it's the scaffolding of the universe. According to decades of observations, galaxies need this mysterious substance to counteract the explosive force of their own stars. Without it, the Milky Way's rotation would fling its stars into the void like a shattered pinwheel. Yet Dragonfly 44 and others like it spin calmly in defiance of this rule, their stars moving far too slowly to stay bound without dark matter's gravitational anchor. It's like finding a skyscraper standing tall with no steel frame, bricks floating in perfect formation against all physics. Theories abound to explain this cosmic heresy. One camp argues these galaxies did have dark matter, only to have it ripped away by a violent encounter. Picture a smaller galaxy plunging through a dense cluster, its dark matter stripped like sand in a tidal current, leaving behind a skeleton of stars. Others propose these galaxies formed in rare pockets where dark matter was oddly scarce from birth, cosmic deserts where the usual rules didn't apply. But the most provocative idea, that ultra-diffuse galaxies are the corpses of once normal galaxies, their dark matter evaporated by some unknown process, like ice melting into vapor. The plot thickens with discoveries like NGC 1052DF4, another dark matter-deficient galaxy where stars roam freely, unbound by gravity's usual chains. Its existence deepens the mystery. If these galaxies lost their dark matter, why do they still hold their shape? Shouldn't they have disintegrated into stellar streams by now? Some theorists suggest alternative gravity laws, modified Newtonian dynamics, or might explain their stability without invoking dark matter at all. But MND has its own flaws, struggling to account for larger-scale phenomena like galaxy clusters. What makes Dragonfly 44 and its kin so revolutionary isn't just their strangeness, it's the questions they force us to confront. Are we missing something fundamental about dark matter's behavior? Could it interact with itself or decay over time in ways we've never imagined? Or worse, are these galaxies the first hints that our entire cosmological framework needs a rewrite? Every new ultra-diffuse galaxy discovered adds another piece to the puzzle, challenging us to rethink the invisible forces shaping the cosmos. And until we solve it, these ghostly giants will keep hovering at the edge of our understanding, whispering secrets that could unravel the universe as we know it. Somewhere beyond Neptune, in the frozen outskirts of our solar system, an invisible force is tugging at distant worlds, bending their orbits into patterns that shouldn't exist. This is the heart of the Planet 9 hypothesis, a tantalizing clue that something massive, something unseen, might be lurking in the darkness. The story begins with a handful of icy objects in the Kuiper Belt, a region of space filled with dwarf planets and cosmic leftovers from the solar system's birth. These objects don't behave like they should. Instead of following random, scattered paths, their orbits tilt and cluster in a way that suggests the gravitational hand of something far larger, something at least 5 times the mass of Earth, silently shaping the outer solar system like an unseen puppeteer. Astronomers Konstantin Batygin and Mike Brown first proposed Planet 9's existence back in 2016, not because they saw it, but because the mathematics demanded it. Take Sedna, for example, a dwarf planet with an orbit so elongated that it takes 11,000 years to circle the Sun, or the way a group of extreme trans-Neptunian objects all swing outward in the same direction, like compass needles pointing to an invisible magnet. These anomalies defy coincidence, yet years of searching with telescopes like Subaru and Pan-STARRS have turned up no obvious planet, so where is it? The hunt has led to some wild possibilities. One radical idea: maybe we're not looking for a planet at all. Some theorists suggest Planet 9 could instead be a primordial black hole, a relic from the Big Bang no larger than a grapefruit but containing several Earths' worth of mass. These ancient black holes, if they exist, would be nearly impossible to spot directly, but their gravitational influence would mirror that of a hidden planet. Astronomers have even proposed scanning the sky for brief flashes of gamma rays, the telltale signature of dark matter annihilating in the black hole's crushing grip. It's a long shot, but in a search this elusive, every possibility matters. Then there's the rogue planet scenario. What if this isn't a native of our solar system, but a free-floating world captured by the Sun's gravity long ago? Simulations show such events are rare but possible, especially in the crowded stellar nurseries where young stars form. A captured planet could explain why we haven't spotted it yet. Its orbit might be wildly inclined, or it could currently be hiding in the glare of the Milky Way's dense starfields. Of course, skeptics argue the orbital oddities might have simpler explanations. Could gravitational interactions among Kuiper belt objects themselves create these patterns over time? Or is our data simply skewed by observational biases? After all, the outer solar system is vast, and we've only mapped a tiny fraction of it, the Vera C. Rubin Observatory, set to begin sweeping the skies in the coming years, could settle the debate once and for all, scanning for faint movements against the starry backdrop. What makes the Planet 9 hypothesis so captivating isn't just the potential discovery, it's the audacity of the hunt itself. Here we are, in an age where we've photographed black holes and landed rovers on Mars, yet our own cosmic backyard might still hide a giant, unknown neighbor. Whether it's a planet, a black hole, or something even stranger, the search reminds us that the universe always keeps a few cards close to its chest. And until we find or rule out this hidden world, it will linger at the edge of our imagination, a ghost in the celestial machinery. From the eerie silence of the Boötes Void to the unexplained acceleration of the Pioneer probes, from the impossible geometry of Saturn's Hexagon to the fleeting whispers of the WOW signal, every discovery we've explored today is a humbling reminder that the universe operates on a scale of mystery we're only beginning to grasp. These 30 cosmic enigmas aren't just anomalies, they're doorways to questions we haven't even thought to ask yet. Each one challenges the boundaries of our understanding, proving that for every law of physics we've written, there's a corner of the cosmos where the rules don't apply. Think about the implications: black holes that sing, galaxies without dark matter, stars that vanish without a trace. These aren't just curiosities, they're clues that the universe is far stranger, far more inventive than our textbooks dare to suggest. The very fact that we've stumbled upon these mysteries means there's so much more lurking just beyond the edge of our instruments, waiting to defy logic all over again. And that's the real magic here, not the answers we've found, but the questions we can't yet answer. So what's next? Maybe you'll be the one to spot the next great cosmic contradiction, or perhaps you'll wake up tomorrow to headlines about a new discovery that rewrites everything. That's the thrill of living in this golden age of astronomy. where every telescope, every algorithm, every curious mind brings us closer to revelations we can't yet imagine. The universe isn't just a static backdrop, it's a living puzzle, and we're all piecing it together, one paradox at a time. Before you go, let's keep the conversation spinning. Drop your favorite cosmic mystery in the comments. Was it the diamond planet burning in its own sky, or the galactic ghost ship Oumuamua, or maybe something we didn't cover that keeps you staring up at the night sky wondering? Because the greatest lesson of all, however much we learn, the cosmos will always find a way to surprise us, and that's what makes exploration so endlessly exciting. The universe isn't just out there, it's inviting us to look closer, think deeper, and stay forever curious. So here's to the next great enigma, and to the minds bold enough to chase it. The stars have secrets, and we're just